Welcome to a special segment of Oh Come On! Today we will be going over Chapter 16, Activity 6, which is all about conjugated pi systems and pericyclic reactions. So let's get to it. On your worksheet and you're good to go. So key point number 1. In a Diels-Alder reaction, the reaction is made facile, which means easier fast, if the diene has an electron donating group and the dienophile has an electron withdrawing group. Notice how atoms 1 and 4 on the diene are interacting with the dienophile. Let me point to that with my laser pointer. So here is number 1 as I'm circling over here, and number 4 of the diene. So now we're on to question number 1. Instructions are: select the atom 1 or 4 of the following dienes with the most electron density. To do this, draw the resonance structures of the following dienes. Part B is to select the atom of the dienophiles with the least electron density. To do this, draw all the resonance structures of the dienophiles. Now, since we have went through resonance structures throughout all of our chemistry courses, this should be review, hopefully, for all of us. So I'm going to go through this rather quickly with a brief explanation. So for the first diene you see here, do you notice where the allylic lone pair would be? So here, lone pair is going to be on the nitrogen, and you will notice that this is an allylic lone pair resonance pattern in which this lone pair goes down to create a double bond, and this double bond breaks to create an electron lone pair on carbon number 2. This results in nitrogen having a positive charge and carbon number 2 having a negative charge. Now you will notice that it's the same exact pattern as the one we've done in the first one. So let's do it again. The allylic lone pair goes down to create double bond breaks, create an electron lone pair on carbon number 4. Hence, you now have a negative charge on carbon number 4, making carbon number 4 the location with the most electron density. Now on to our next diene. You notice that it is symmetrical. If you draw a line through here, it's going to be the same carbons. Whether you flip this around, turn it around, whatever you do, it's going to be the same carbons, same effects, with equal electron density. Also, I forgot to mention, on the previous diene, notice that we are only focusing on either carbon number 1 or carbon number 4. Even though carbon number 2 also bears a negative charge on one of the resonance structures, it's not necessarily important in the Diels-Alder reaction. Carbon number 2 or carbon number 3 is not going to be key factors in our Diels-Alder reaction. We're only focusing carbon 1 and carbon number 4. So please remember that key point. So onto our dienophiles. So on the first one, same thing, symmetrical. Draw a line through here, and you're going to notice that this carbon and this carbon are going to have the same exact electron density. None of them are more or less than each other. And notice that we also use only the carbons that are directly attached to the double bond right here as I'm pointing. So onto our next dienophile. Here, oxygen is more electronegative than carbon, so the double bond breaks to give an electron lone pair to oxygen, making oxygen have a negative charge. Then the double bond breaks here to create a positive charge on this carbon. Hence, this carbon over here has the least electron density. question number 1 continued. Let's look at our dienes on the left-hand side. Same thing, like lone pair breaks apart. Not necessarily breaks apart, I'm sorry. The Lilic lone pair goes down to create a double bond here. Then the double bond here breaks to create a lone pair on the first carbon. Hence, the first carbon here is going to be your carbon with the most electron density because it's the one that's bearing a negative charge. And really remember your resonance patterns and how the arrow mechanisms work, because notice here you can't suddenly have this allylic lone pair go down over here and then break apart here. It doesn't make sense to break the bond between number 2 and 3, because remember, only the pi bonds are going to be breaking and not the sigma bonds, aka the single bonds. Should never do that. So on to our next diene. Same thing, like lone pair on the oxygen goes down to make a double bond breaks, create a negative charge on this 4th carbon, making this 4th carbon have the most electron density. Then on to our next diene. It's completely symmetrical. Now notice here that it looks not exactly like how our usual dienes would look like. However, if you rotate the sigma bond over here, you can actually make it an S-cis formation, which is very important. Diels alder is that they need to be an S-cis, so this still works. For this one, it's going to be an equivalent carbons. Whether you do this one or this one, it's going to be the same thing. They both have the same amount of electron density because they're all surrounded by carbons. Now onto our dienophiles. So here is the same pattern as the previous slide. Oxygen, I believe it's the same one as the previous slide now I think about it. What happens here? Double bond breaks to give oxygen the most electronegative in this structure, a negative charge. Double bond breaks over here and creates a positive charge on this carbon, making this carbon the one with the least electron density. And over here, I redrew it so you would see exactly where the triple bond is on the carbon and nitrogen. So here what happens is nitrogen, the most electronegative in the molecule, gets the electron pair. So here the bond breaks, gives a lone pair to nitrogen, making nitrogen have a negative charge. Then the double bond breaks over here, transfers over, and creates a positive charge on this carbon. Now notice this carbon has the positive charge, hence this carbon over here is the one with the least electron density. Our next dienophile, same pattern as before, so I won't go to detail about it, but here this carbon is going to be the one with the least electron density because it bears a positive charge over here. Same thing over here. Double bond breaks to the oxygen to give a lone pair, creating negative charge. And and then the double bond breaks over here, transfers over, creating a positive charge over here, making this carbon the least electron dense. This brings us to key point number 2. The electron donating group and electron withdrawing group will dictate the regioselectivity of the Diels-Alder reaction. Once again, in a Diels-Alder reaction, the carbon atom of the diene with the most electron density will interact with the carbon atom of the dienophile with the least electron density through Coulombic attractions. Flip the dienophiles vertically upside down to obtain a matched case where both the partial negative and partial positive are in close proximity. So on this little diagram over here, notice here that on this diene, this carbon is going to be the one with the most electron density as the one that's covered in a huge black circle. And then in the dienophile, this carbon is going to have the least electron density. But here there is a mismatch because the one with the most electron density on the diene is not in close proximity with the dienophile's least electron dense carbon. They are diagonal from each other. They should be next to each other. So here we just flip this molecule, the dienophile, and now they're in close proximity and a Diels-Alder reaction can now take place. So this goes on to our next question. Question number 2. Ignoring stereoselectivity, predict the product of the following Diels-Alder reaction. Remember to consider if the partial negative and partial positive charges are in close proximity. If not, flip the dienophile upside down. So here, let's take a look. Remember resonance structures all the time. We're doing it for both the diene and dienophile to determine where or what the product will look like. First, like lone pair goes down, create a double bond, and the double bond breaks to create a electron pair on carbon number 2. Same exact pattern on resonance structure number 2. And in the end, you get a negative charge on the 4th carbon. Let me point to it. So here, negative charge on this carbon, which makes this carbon, carbon number 4, the most electron dense. Now on to our dienophile. Notice that it's symmetrical. Draw a line down here. And you'll notice that whether you use this carbon, carbon is gonna make no difference. As a result, the product is this one you see over here. And if you're wondering how exactly did we get this product, let's have a little concept review. And you can review from Chapter 16, Activity 5 to revisit this topic. So I'm going to briefly go over it. So electron donating group over here on the diene. And here's the dienophile with the electron withdrawing group. So here you notice that you can go clockwise or counterclockwise, but they should go either any of those directions. So here, double bond breaks from this dienophile, creates a sigma bond over here, double bond transfers over to between carbon number 2 and 3. Carbon number 4 of the diene breaks apart to create a sigma bond between the diene and dienophile. And hence, if you just like connect between carbon number 4 and this carbon and carbon number 1 and this carbon on the dienophile and transfer over the double bond, you will get this product. Take some time to visualize that and the rest will come to you. So on to our next pair of molecules. Notice that this one is symmetrical, draw a line down here. It doesn't matter whether you use this carbon or this carbon. As for the dienophile, draw the arrow from double bond to this, and the double bond breaks to create an extra lone pair on oxygen, making this carbon the least electron dense in the dienophile, because when you draw out the resonance structures, you'll notice that this has the positive charge. So the product will look like this here. And again, we're ignoring stereochemistry. Next problem. Like lone pair, oxygen goes down to create a double bond breaks and transfers over a lone pair onto this carbon, carbon number 1, as I usually number this one, and this will bear the partial negative charge then, so it's going to be the most electron dense in the diene. Dienophile, same exact pattern as the previous pair of molecules. So this one over here has the partial positive charge, the least electron dense. Now notice here that these two carbons, the one with the most electron density and the one with the least electron density, are not in close proximity to each other. They are not directly next to each other. So that means for the dienophile, you need to flip it. And when you flip it, this is what the molecule is going to look like. Carbon is now going to be right next to the diene with the most electron density carbon. So here and here, now they're next to each other, it's ready to go. And so our product is going to look like this. Notice now the oxygen from the dienophile is going to be over here because you flipped the molecule. That's very important, is that once you flip the molecule, it's going to look different from when you don't flip it. And the one that's flipped is the correct product. Now, question number 2 continued. So here's our dienes, and these are our dienophiles. So get straight to it. This is the one with the partial negative charge. Again, resonance structures. You're going to find that the negative charge, when you draw it, is going to be on this carbon. Partial positive charge on the dienophile is over here. Notice that they are directly next to each other, so there's no need to flip the dienophile. So let's keep on going. Your product is going to look like this. Next one, notice that this one is symmetrical, the diene, but you need to redraw it so it's in an S-cis formation. Because remember in Diels-Alder reactions is that it cannot be an S-trans in order for it to work. because it'll be too far away for any reaction to really occur. So we withdraw to a cis formation. And for the dienophile, partial positive charge when you draw the resonance structure is going to be located on this carbon over here. This makes the product look like this. Now for the next one, remember what I said for the previous problem? It has to be an S-cis formation. And sometimes you can twist the sigma bonds, like in this one, to make it S-cis. But for this one, when you look at it, can it rotate the sigma bond over here to make it S-cis formation? The answer is no, cannot. It's wrapped in a ring, and you can't rotate rings in a way that you can make it S-cis. So it's forever locked in S-trans formation. So even though this dienophile has an electron withdrawing group, and it's going to have a partial positive charge here, it doesn't matter because the diene is an S-trans. That means you're going to have no reaction. To our next key point number 3. So to determine the stereochemistry of the Diels-Alder product, consider the following model on the right. So after flipping the dienophile upside down, you have to consider flipping it horizontally, so left or right, in such a way that the electron withdrawing group is puckered underneath the diene to benefit from favorable orbital overlap. So use this model to consider the regiochemical and stereochemical outcome of the following Diels-Alder reaction on the next slide. Before I go on to the next slide, let me point to what it's talking about. So here you notice that this functional group over here is your electron withdrawing group. So you want this electron withdrawing group to be right beneath where the pi bond over here would be forming. So as you see here, there's going to be a carbon double bond over here. So you want that electron withdrawing group from the dienophile to be right beneath it, because that's going to be your thermodynamically favorable product, which is called the endo product. The kinetically favorable product that you are usually not going to draw because it's not selective is the exo product, in which you notice here the electron withdrawing group over here from the dienophile is not beneath the developing pi bond. It's far away, which means it's not going to be thermodynamically favorable. So notice the difference here and here, where the location of electron withdrawing groups are. So be mindful to recognize that the electron withdrawing group must be placed on the face of the dienophile that is closest to the diene, so the molecules can have favorable orbital overlap. So let's take a look at this model as you see over here. Here we need to flip this molecule as we've done in the previous questions, because the partial negative and partial positive needs to be next to each other. So there we go, we flipped it. Now we have to flip it left or right now. That's the difference between this question and the previous questions we did, is we didn't flip it left or right, we just flipped it up or down. So another step to do is flip it left or right for the dienophile, so the electron withdrawing group is pointing towards the diene. So here we go. Now this electron withdrawing group is pointing towards the diene. And this model can now be used to predict the stereochemistry. I know it's a lot to take in, but I will go through this slowly so you can understand this very thoroughly. So question number 3. The product from the previous slide, as I drew over, or I put on this slide again, this original product, is drawn from the perspective of the dienophile coming into contact with the diene from below it. Now draw the stereo product where the dienophile is coming from the top. What is the stereochemical relationship between the two products? So this is all just about visualization and knowing where your dienophiles are going to be coming into contact with each other. So I'm going to go through this quickly. So this is what's going to look like when your product is, dienophile, is coming from top. Is now they're both on wedges. So what does this mean? Notice here, these two substituents are both on dashes. For the other product that's coming from the top, they're both on wedges. So what does this mean? That means they are mirror images of each other that are non-superimposable. And this is called an enantiomer. That's the relationship, is that they're enantiomers. And then our next question, our last question, is question number 4, which is to predict the product of the following Diels-Alder reaction. Make sure to indicate stereochemistry wherever applicable. Remember to consider both regioselectivity and stereoselectivity. So our first set of molecules, we're going to notice after making the resonance structures that the partial positive and partial negatives are right here. They're right now directly next to each other, and this is already puckered in, facing towards the diene, this electron withdrawing group of the dienophile. So you're good to go to make the product. It's going to look like this. And of course, do not forget plus En, which is plus enantiomer, because you can make this one a wedge and this one a dash, because it can come in from either the top or bottom. So remember that. And this one, diene, we're going to redraw it, so it's an S-cis formation. It's going to look like this. Notice that the partial negative charge, the most electron dense region, is on carbon number 1 over here. The dienophile, this is the one with the the least electron density based on your resin structures that you drew. We're going to redraw this so that this is facing the diene, because we want the electron withdrawing group to also be facing the diene. So we're flipping it left or right now. Now in this case, we're flipping it to the left. And it's going to look like this. This makes our product. And of course, don't forget this En is your enantiomer. Over here, partial negative charge over here, partial positive charge over here. They're next to each other, so you're good to go. You don't need to worry about flipping it really left or right. So this is your product. Now you're probably wondering, how did I know where the wedge and dash goes? I think a lot of people have trouble knowing which one goes on the wedge or dash because they have trouble visualizing. It takes some time. Some people use model kits to visualize it, and some people use their fingers. For me, after I learned how to visualize it, like know how it actually works, which takes some time really. I go through it really fast because I find out patterns between all of these molecules and what's happening in the reactions. So I created some key points for you to look at so that it would be much quicker to do these mechanisms, because I know if you don't always have a model kit with you, and if you do, it'll take too long on exams. So here are some shortcuts. Key point number 4. So when drawing this, you have to notice what is on the same side. So what's considered on the same side of the product is 1, the outside group of the diene, and the electron withdrawing groups and substituents that are cis to the electron withdrawing group of the dienophile. Then you also want to draw those on the same side with a dash. And the remaining active substituents of both diene and dienophile go on the wedge. So this goes to the next point. Then how do you know what's going to be flat and planar? What's going to be a straight line, not a wedge or a dash? So everything that is not directly connected to the 1,4 carbons of the dienes are going to be flat and planar. This also includes what I call the faraway bonds of the dienophiles. So this means like the ones that are not directly part of the carbon-carbon double bond. They are the faraway bonds that, you know how you look onto a shore, if you're nearby, everything seems 3D, but you look far away, they all just look flat and the same. That's how you can think about the dienophile. Those are not directly on the double bond. They can be flat and planar, or they're not what I call the active substituents. So let's take a look on here. Here, highlighted in yellow, hopefully you can see it. That is going to be your outside group of the diene that I'm talking about. So the outside group is the one that sticks out of the diene. And here you have electron withdrawing group right here. And this is what's cis to the electron withdrawing group. So over here, this correlates to the product. As we said before, we're going to standardize this all just for easier purposes, is that everything goes on a wedge for on the same side substituents. So here, notice that the outside group of the diene goes over here. What's cis to the electron withdrawing group of the dienophile, as well as the electron withdrawing group itself, they're right here. Now notice everything else that's not actively part of it are flat and planar. So this means the ones that's carbon number 2 and 3, as well as the ones that are after this carbon. They all go flat and planar as well. Now, also you should notice that what goes on the wedge is everything else that are the active substituents. So here, this goes on a wedge. As seen over here, that's what I call the inner group that's attached to carbon number 1. Here, although we don't really draw in hydrogens, for this purpose, we're just going to draw them in so you can understand where they go. Highlighted in pink, they are the active substituents that do not follow these 2 criteria. So there's the hydrogen on the wedge and the other hydrogen on the wedge. So hopefully that helps a little in these Diels-Alder reactions. So let's continue on to the rest of the questions. Here is where your partial negative charge is going to be. This one's symmetrical. Draw a line through this. Use this carbon, this carbon. It's going to be the same thing because they both have the same electron withdrawing groups. So your product is going to look like this. And of course, plus En. Once again, notice this is puckered outside. Or not puckered, it's sticking outside of the diene. That's going to be on the dash. Over here, electron withdrawing group, electron withdrawing group. So, dash here, dash here. Then you're also going to notice that over here and over here is your inner groups of the diene. So that's going to be on the wedge. And the rest go on flat and planar because they're far away or they're non-active, what I call non-active atoms of the molecule. So this one, we're going to redraw it. It's right now an S-trans. This is where the partial negative charge is going to be after drawing the resonance structure. Here's where the partial positive charge is on the dienophile. You'll notice you need to flip it because here the partial negative and here the partial positive are not directly next to each other. So we're going to flip that. Once again, this is what your product is going to look like. This is tert-butyl group, so it's the same thing over here, just abbreviated over here. So your electron withdrawing group and what's sticking outside of the ring of the diene both go on dashes. And of course, that's En, which is an enantiomer. Now all the rest that are hydrogens that would be attached over here and here, we don't draw them in, but if you did draw them in, they would be in wedges. The next one, there is your most electron dense. Here's your least electron dense. They're not next to each other, so you need to flip the dienophile, make it next to each other, and then your product's going to look like this. Very complicated, but if you apply the same principles that I've mentioned before, you should be able to get this product. Problem, notice that this molecule is symmetrical. Draw a line across here. It's going to be the same carbons that you can use either or. This one also has symmetry. So your product in the end is going to look like this. So over here, this is considered an inner group, the ones that are not sticking out of the diene. So they're going to be on the wedge right here. So this little 3D shaded region, that is your inner group of the diene. That used to be the part of the diene. And then also, don't forget, plus E. With that said, everyone, thank you so much for listening to my special segment of OK.